Hola Ana,
Hola Manuel, ¿qué tal?
¿qué tal? ¿Cómo estás?
Muy bien.
Bueno, bienvenidos a todos. Tenemos una nueva actividad como parte del programa público de actividades de la Escuela de Arquitectura y Estudios Urbanos de la Universidad Torcuato Di Tella. Hoy vamos a continuar con el ciclo Archivo Redux, que está coordinado por Ana Font, que también es coordinadora del Archivo de Arquitectura y profesora de la escuela. Eh, Archivo Redux es un ciclo en el cual se transmiten registros y ediciones realizados por el Archivo de Arquitectura de actividades curriculares y extracurriculares de la Escuela de Arquitectura y Estudios Urbanos en los últimos años. Se reviven las ideas que circularon y fueron debatidas en la escuela en su historia reciente. Los contenidos editados son presentados nuevamente, renovando su interés cultural y potenciando su influencia disciplinar mediante su recontextualización temporal, y las transmisiones construyen progresivamente una taxonomía de la cultura contemporánea mediante la singularización y la organización retrospectiva de los posicionamientos, prácticas, discursos y sensibilidades que han discurrido a lo largo de estos años recientes. Hoy tenemos una conferencia que dio David Benjamin, Adaptation, el 17 de octubre de 2016.
Sí, vamos a 2016 esta vez esta conferencia que, bueno, David Benjamin es fundador de The Living, que es una oficina neoyorquina y habla, la conferencia está centrada en su práctica, pero a nivel del Redux, y decías esto de la taxonomía y creo que, bueno, para mí es muy importante centrarlo en ese lugar, ¿no? ¿Por qué estamos viendo esta conferencia de 2016 de David Benjamin, ¿no? Y el marco en el cual hablamos hace un mes ahora, la conferencia anterior en la cual empezamos a sacar este tema de el New Climate y las prácticas ecosistémicas y también las prácticas materialistas, que es como un thread que estamos construyendo en esta idea de generar vínculos que saltan años y que nos permiten entonces configurar una idea no cronológica de esto que estamos llamándole como estas prácticas que están vinculadas. Lo que vimos hace un mes fue Trópico Canónico de Camilo Restrepo, que es un par que hicimos con Christopher Haidt y la arquitectura del Antropoceno, y a ese par estábamos como poniendo al lado el par de las prácticas ecosistémicas, que sería esta conferencia de David Benjamin, y el próximo semestre una conferencia de Marco Poletto de Ecologic Studio que se llama Polycephalum. Y lo que estamos construyendo con estas dualidades que se encuentran y resuenan entre sí es abrir este espectro de diferencias, digamos, en un campo que a veces puede ser también englobado, pero que tiene profundamente como mucho nuance interno. Y en el caso de la idea más ecosistémica, la práctica de living está muy fundada en la construcción de prototipos, por ejemplo, a escala real, mientras que en la práctica que vamos a ver de Ecologic Studio funciona a escala territorial, a nivel construcción de relaciones sobre mapas, y después también construyen condiciones prototípicas, si se quiere, pero más como test de sistemas de funcionamiento mucho más basados en fluidos, ¿no? Como tienen una idea de experimentación muy distinta. Entonces, me gustaría sentar hoy ese par, que más allá de que lo vamos haciendo como el Redux cada 2 semanas, se generan estos lapsos de un mes, un semestre, pero vamos a ir como picking up en eso. Y el otro link que se está abriendo hoy, porque avanzamos, estamos en el medio, justo hoy estamos en la cuarta conferencia de las 8 de este semestre, es el link que vamos a saltar a buscar después, que es el de las prácticas materialistas, donde vamos a ver una conferencia de Sergio Araya y otra de Sebastián Curián. Y para mí en ese encuentro me resuena también una condición de los tipos de experimentación que implican y de la suciedad, diría, de la experimentación, de la suciedad, digamos, del dirt, digamos, vinculado a la experimentación. Porque como vamos a ver hoy, es una práctica como muy limpia, muy neat, de ideas como muy tecnologizadas. de procesos que están como en un estado parecería consolidado y que su experimentación ya está funcionando adentro de unas técnicas que están como muy, no sé, o digamos, con mucho funding o con mucho recurso de que puedan ser revisitadas. Entonces, esa condición me parece que simplemente la quiero como poner ahí y decir, bueno, ¿qué sucede con estas prácticas que se ubican en esa situación y que les gusta, digamos, diseñar los procesos que son en sí como generan cierto estilo de belleza, digamos, ¿no? Para no generalizarlo a una belleza absoluta. Entonces, bueno, esa es un poco la propuesta, que es verlo en fricción con una práctica más de ecosistemas como dinámicos y unas prácticas de pensamientos materiales un poco más sucios, más de procesos más mediados por la materia y menos por la tecnología. Y dentro de eso, en todo caso, quería introducir un poco antes de que empecemos con la conferencia, algunas ideas que van a poner sobre la mesa. La descripción de la arquitectura según David Benjamin y su práctica es un entendimiento de los edificios como organismos vivos, unos organismos que tienen un metabolismo propio, y hace mucho énfasis en la idea de loops interconectados, que es una manera de no decir sistemas, ¿no? Me parece, o sea, habla de loops y esos, las relaciones entre ellos son lo que considera una arquitectura que tiene sentido. Explícitamente dice como que la tecnología sin la cultura no tendría sentido, el ambiente sin la justicia no tendría sentido, o los humanos sin los no humanos no tendrían sentido. Entonces, habla en términos de ingredientes mucho y de combinatorias. Creo que hay una tendencia a poner juntas cosas y al ponerlas juntas hay una cierta didáctica en juego que está presente a veces de manera más explícita, como con la idea de los sensores, proyectos que prototipan ciertas condiciones y deploy sensores de data que después emiten luz y emiten señales, emiten mensajes, y hay una comunicación implícita, hay una voluntad de comunicar la medida de la data, como de medir data en el sentido de polución del aire, polución del agua, ¿no? Hay una primera etapa donde vamos a estar viendo cómo el proyecto prototipa un artefacto que permite entonces recoger una información y comunicarla, ¿no? Entonces esa es una de las ramas de esas tecnologías que estaba introduciendo, como si procesara algo que después tú puedes consumir. Después hay una segunda platea, digamos, que es la de la simulación de organismos vivos que tienen ciertas capacidades de networking y de constitución de complejidad, que entonces devienen modelos para construir piezas metálicas, por ejemplo, en el caso de un Airbus, un trabajo que hicieron con Airbus, que se vuelven altamente eficientes y pueden regular una cuestión de mínimo peso y mínima, digamos, esfuerzos a carga de compresión, y lo que hace ese modelo es como volver tecnológica un comportamiento biológico que ellos sintetizan y vuelven como un algoritmo, ¿no? Entonces es como una segunda, es un segundo tipo de proyecto que va a presentar. Y el último tipo de proyecto que va a presentar en esta conferencia, que es de 2016, es una especie de nuevo ladrillo, que es básicamente constituir un material que en sí está hecho como de reusado y genera ciertas formas, que esas ciertas formas generan unas pequeñas, digamos, desplazamientos de cómo se apareja el ladrillo, pero bueno, es un proyecto para el PS1 que es como muy, digamos, muy conocido y que genera, bueno, ese diálogo con el tema del reuso. Ahora, si uno entra a ver sus trabajos más recientes, vamos a ver trabajos de Machine Learning, de retratos, de mirrorings, de distintos tipos de registros de caras de personas, o proyectos generativos con Autodesk, de layouts de oficina que generan una multiplicidad de opciones, ¿no? Y transgreden ciertas lógicas que parecen más establecidas. Entonces, traigo esto digamos, hacia dónde sigue, porque me parece que es como una práctica que no volvemos a ver otro material rediseñado como el del ladrillo, no volvemos a ver otro proceso biológico recomputarizado, o no volvemos a ver un showcase de data recogida y expuesta, sino que sigue siempre como hacia lo nuevo, pero ya como un nuevo que ya está establecido, ¿no? O sea, una práctica que está al día de la experimentación oficial, digamos. Cuando esa experimentación ya es oficial, está ahí y la hace como neatmente y la ejecuta nada, como la ejerce, digamos, ¿no? Ejerce la experimentación. Entonces, me parece que eso, por lo pronto, es un tipo de condición que tampoco es tan habitual en un punto, ¿no? O sea, no hay tanto de eso. Es muy neoyorquino como cultura, también me parece, como de la cosa que cierra y cierra, por lo pronto, tiene un cierto political correctness, tiene una cierta extensividad, pero tampoco falla, ¿no? Como que tiene la posibilidad de transgredir algún tipo de threshold un poco lejos, ¿no? Entonces, nada, me parece que eso que en esta práctica puede ser más explícito, en otros también por maneras de presentarse voluntariamente más convoluted, no es tan obvio, pero puede ser que también tengan esas tendencias, y no lo estoy exponiendo como una desvalorización ni mucho menos, sino como algo que estaría bien poder hablarlo, poder decir en qué consiste la potencia, digamos, de operar en ese marco o no, ¿no? Y hacia dónde se tensan los descubrimientos que en un momento son muy, digamos, reveladores. ¿Qué futuro tienen esos descubrimientos? ¿Hacia dónde se los tensa? ¿Qué producen cuando se establecen? ¿Qué le devuelven a la práctica? ¿Qué le devuelven a la disciplina? Porque hay algo de eso que es muy poco fashionable, ¿no? Porque es o lo nuevo o si no, lo más, lo anterior, pero hay un espacio gris en el medio. Entonces, me parece interesante traer este problema, digamos, al ver esta conferencia, volver a verla y nada, discutirlo en esos términos a lo mejor, ¿no? Como una de las maneras de verla.
Me parece muy interesante, por empezar, cómo se va construyendo o explicitando la construcción de la serie, de las distintas conferencias. O sea, hubo varias cosas que dijiste que me parecían muy interesantes, quizás yendo como del principio, no sé, digamos, ¿podrías desarrollar un poco más la diferencia entre una experimentación sucia y una experimentación limpia? O no sé cómo sería, digamos, eh, porque me parece que no, en algún punto tiene la cosa obvia de que realmente sea sucia, como en un sentido higiénico sucia, como materialmente sucia, eh, pero después creo que eso se vuelve un modelo para otros tipos de experimentaciones, no sé, digamos, con materiales menos tangibles, como dibujar o escribir o, no sé, sacar fotos, no sé, una cosa así. Eh,
Sí. Sí, no me parece que, sí, sucio parece que implica algo manual, pero sí, no me referiría a una cuestión literalmente manual, sino sucio a lo mejor en sus idas y vueltas, ¿no? En su construcción como pensamiento que necesariamente si está emergiendo digamos, de una transformación que va de bien en algo, hay una suciedad en ese devenir que es casi imposible de evitar, ¿no? Hay como una condición del pensamiento que a veces tiene eso, y no lo digo místicamente tampoco, creo que hay nada, uno que lo ve de lado y dice, claro, esto tiene estos problemas, se reconoce a sí mismo dentro de esos problemas, ¿no? En cambio, esto parece como tener un estado etéreo de que no hay, ¿sabes? No hay como una fricción, no hay, sí, por ahí es eso también, como no hay una fricción porque esto en sí está bien, digamos, ¿no? Es así.
Me pareció buenísimo cuando lo decías, porque sí, digamos, incluso me da ganas de pensar, de seguir pensando en esos términos. en si es la relación entre sociedad y experimentación, sin, obviamente sin caer en las figuraciones o los clichés de eso, ¿no? Como por decir algo como la bohemia, ¿no? No por un problema de eso. No, pensaba, hay algo como que la experimentación, eso que uno ve como sociedad, también puede ser como el espacio que deja abierto para incorporar diferencia,
Ujú.
¿no? Digamos, como eh, en un dibujo se ve muy simple eso, ¿no? Como si uno ve un cuadrado, es poco sucio, digamos. Están esas, hay algo como de visualmente limpio o puro. eh, y en este caso que vos decías me parece interesante. Ahí creo que se relaciona con otra cosa que decías, que es cuando la experimentación se instituye o se establece, se vuelve oficial, decías, que es también como se vuelve un commodity, digamos, se vuelve... eh, sí.
Sí,
La vez pasada hablábamos sobre Deleuze, ¿no? Y en la conferencia era sobre Deleuze. Hay algo que dice Deleuze que no recuerdo ahora dónde, pero creo que es en las clases sobre pintura. Varias veces dice, está a punto de arruinarse. Entonces encuentra el interés en lo que está a punto de arruinarse. Como un poquito más se arruinaba. Eh, Me parece que hay algo de eso, como de que la experimentación requiere de ese horizonte. Si no es otra, digamos, si no es otra cosa.
sí, sí, me hacías pensar específicamente, por ejemplo, en el proyecto que decía este de los ladrillos, que, que al producirse el ladrillo como objeto, la forma que tiene por cómo el material está orgánicamente evolucionando en su proceso de gestación, tiene una forma que genera problemas de correspondencia de los planos, ¿no? Por ejemplo, en ese instante, creo que hay muchas maneras de reaccionar a ese problema, ¿no? La reacción de este proyecto es como tecnologizar todos los encuentros de modo que minimicen ese espacio de diferencia, de modo que los apoyos, ¿no?, tengan como ciertos tantos por cientos y tal, pero por el lado de optimizar el problema del apoyo de un ladrillo sobre el otro, está dejando de lado la construcción del problema, que puede ser la construcción donde está el proyecto. O sea, en lugar de pensar que el proyecto está en esa no correspondencia absoluta, esa no industrialización, ¿no?, de dos planos paralelos lisos que necesariamente construyen esas condiciones, sino que al haber sido producido el ladrillo por un proceso orgánico tiene ciertas diferencias, esa diferencia es un trigger de un trabajo al que lo estamos llamando, en este caso, sucio, porque va a seguir explorando en ese lugar hacia dónde hacia dónde puedes transformar las relaciones entre ladrillos, no solamente ya el ladrillo, sino sus relaciones, y cómo, hasta qué plano puedes tensarlo. Entonces creo que ese es un ejemplo, digo, para poner un ejemplo también no sé a qué me refiero en este instante, ¿no?, que sería, bueno, no retecnologizar todos los encuentros para poner el ladrillo más adecuado, sino seguir expandiendo el problema de la relación entre ellos e incluso liberar ese lugar, ¿no? Entonces esa tecnologización es lo que me parece que tiende a homogeneizar y tiende a deconstruir el problema que se había construido por el proceso biológico y realmente, ¿no?, como generativo, ¿no? Entonces el problema de la emergencia está muy controlado, hay como un control de lo emergente que es eso, ¿no? Bueno, creo que tú lo estás poniendo ahora en los términos de Deleuze, que me parece que es parte de lo mismo.
No, digamos, me parece que es interesante cómo incluso un concepto como el de emergencia implica una tercera cosa, etcétera. Digamos, es como una alternativa a la indeterminación y es una salida del determinismo, etcétera. Puede volverse, incluso se puede codificar y volverse, quedar reinscripto o reabsorbido por su opuesto, no sé, o por lo que no lo contiene.
Claro.
Justamente en el momento que es predecible, es como está codificada, la emergencia se vuelve no emergente, digamos. No, y después había una cosa que dijiste también, y creo que tiene que ver con algunas conversaciones que venimos teniendo, que hay una afirmación que es tecnología sin cultura no tiene sentido. No, pensaba, no sé bien exactamente en qué consiste, pero no sé si es un fenómeno o algo, o un matiz en los discursos, donde uno puede ver en la afirmación justamente lo que falta, digamos, ver justamente de lo que carece. Seguramente no aplica, obviamente, a toda afirmación, no sé dónde está el matiz, pero no, me parece interesante porque justamente hay algo como no mediado. Sin embargo, me parece que este tipo de prácticas, y esta práctica en particular, tiene una función que justamente, ref- digamos, puede tener su costo y su negatividad, eso, pero refinan herramientas, las introducen y las convencionalizan, las vuelven parte de un discurso oficial justamente, las popularizan, a una escala pequeña obviamente, pero dejan de ser extravagantes. No sé, por ejemplo, ese
Sí,
que vos decías de los ladrillos, probablemente sea posible en función de algo de esta práctica, con una lucha de fuerza seguramente, entre medio, no.
sí, 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 me parece que también se reinscribe muy rápidamente en la Academia Americana, que tiene como cierta avidez por un lado desarrollar y por otro lado refinar, ¿no? Y creo que ahí hay algo también interesante, por ejemplo, en el edificio que hacen en Princeton, que es un edificio de madera laminada, que está como inacabado para que pueda ser un edificio experimentable, ¿no? Donde se pueden incorporar envelopes, donde se pueden, ¿no? Como que los arquitectos pueden experimentar en el propio edificio. Creo que eso reinscribe muy rápidamente como esa cultura de una cierta academia, que creo que ahí a lo mejor también tiene una simbiosis muy interesante, que son los recursos que te decía antes, ¿no? O sea, es una práctica con recursos, fundada en el research y después de comisiones como costosas, y creo que es todo un realm bueno, que es un nicho, ¿no? Es como un espacio que es muy particular en su contexto, que la hace posible, y creo que en eso es singular, ¿no? En la singularidad del contexto que la hace posible, y que le hagan un embracing y que la desarrollen en esos términos, me parece que, nada, es interesante, y vería esta conferencia, y si quieres ahora podemos pasar a verla, y pensaría en cómo evoluciona, porque no es solamente como estos 8 proyectos que va a mostrar, sino que un poco lo que te decía antes, de que van a seguir evolucionando en cierta dirección, ¿no? Y eso es un poco verlos así, no verlos como singles, sino verlos también como serie, y hacia dónde tienden.
Buenísimo. Pasamos a la conferencia.
Bueno, gracias Manuel, nos vemos en 2 semanas.
Hasta luego.
Chao.
Well, thank you very much, and it's a great honor to be here. And as Santiago mentioned, we at The Living, my design studio, we think of cities and buildings as living, breathing organisms. In other words, we think that they have metabolisms, and they have kind of interconnected loops of ideas, technologies, materials, culture, people, politics, humans, non-humans, and the built environment. They combine all of these things. And these interconnected loops are a kind of framework for our design thinking when we approach projects at The Living. In other words, we think of these loops as dependent on one another. Each loop relates to the other loops. For example, technology without culture does not make so much sense. Environment without justice does not make so much sense. Humans without non-humans does not make so much sense. In other words, the the loops and the ingredients of the ecosystem, the ingredients of buildings themselves and cities themselves, make sense through their interconnections. And in that sense also, we think that each of our projects makes most sense through its connection to our other projects and to the work of others before us, and also to the work of others who will come after us. And we very much think about our work in that way, and we design work in that way. So just giving you a sense of the flavor of one of our recent projects, which I won't describe in too much detail, but this is the kind of material stuff of some of our projects recently. And it's kind of in this context, after describing the general approach of the studio, that I want to go into a little bit more detail about several different design approaches that we've been exploring recently in our studio, and I'll show one example project for each approach. And actually, number 0, so kind of the foundation for all of our projects, is prototyping. And this is played out in an approach to research that we developed a few years ago called flash research. So this is a kind of self-initiated research project with 3 kind of qualities to it. The first is self-imposed constraint in terms of time, so we do these projects in 3 months or less. The second is a self-imposed constraint in terms of money. We do these projects with $1,000 US or less. But number 3 is that we also still try to explore an architectural idea through making full-scale functioning prototypes. To give you a sense of what I mean by this, here is the flavor of one of our early flash research projects, in which we made a functioning prototype each week. And each prototype kind of builds on the next in an iterative way, and we kind of learn and decide what to do as we go, informed by the materials on the table, the functioning prototypes. So an example of this is a project that started with a material. This is a diagram of nitinol wire, sometimes called muscle wire. It's basically a thin metallic wire that contracts along its length when you apply electricity to it. And after 3 months spending $1,000 on materials, we came up with this project, which we call Living Glass. So it's a thin, transparent membrane with gills cut into it that can kind of open up and breathe. So the nitinol wire is cast inside this transparent silicone, and it basically gave us a way to explore an envelope or a surface in architecture that can open and close in response to a trigger, such as breathing into the building skin, and it breathes back at you, it opens up. For projects like this, for our flash research projects, we publish materials kind of beyond what a typical architecture project would publish. So we publish not only photographs and kind of videos of the final project, but we also publish things like source code, instruction manuals, circuit diagrams, as a way to kind of offer what we learned for others to build off of. And an example of this is shown in a project by our students at Columbia University, who took nitinol wire and what we had learned and taught them in the first week of class and took it in a totally different direction. And they built this project called the Huggy Wall. We've also kind of expanded on our own flash research project in a kind of larger exploration of some of the issues at stake, and this is a project called Living City. And here we were imagining that as buildings have more and more sensors embedded in them, they might start sharing their sensor data with other buildings, and that usually doesn't happen these days, but it could happen. So more specifically, we went back to prototyping again. We made some low-cost sensors for air quality. We wrote some custom software, and we built a bigger array of our breathing building envelope as a test of this idea that buildings could exchange information. So here kind of zooms in on how we built a sensor for two important qualities of air carbon monoxide and nitrogen dioxide, connected it to a small radio and a battery, and that gave us little sensors that we could deploy inside a building and outside a building, and they could communicate wirelessly. We connected them to a few different building facades, including the Empire State Building shown here. And the data from those sensors was collected through just a cheap laptop and sent through the internet to a gallery in New York City. But to demonstrate the true promise of this, we actually did a second installation where we connected one building in New York to one building in San Francisco, exchanging their local data in real time. And that gives what we think could be a really interesting ecosystem of information to every building. In other words, if every building shares everything it knows with the other buildings, then we can have a kind of exchange, a social network of buildings, and each building alone will have the opportunity to draw on much more information. In other words, we can create a situation where buildings can cooperate with one another to do things like schedule their energy consumption and reduce total peak demand on an energy grid. Okay, so with that as the kind of background for our approach and the kind of foundation of making prototypes, kind of building projects to test them, here I'll start with our 8 different approaches and projects. The first is information, and this is a project that begins with air. It begins with air quality in New York City, in Seoul, South Korea. And here you can see 2 pictures of the same location on different days, and you see obviously there's a great fluctuation in air quality in the city. Seoul already has some really interesting real-time interfaces to air quality, including a digital billboard and some websites. And Seoul also has a kind of building culture of creating building facades with dynamic LEDs. And sometimes these are showing kind of rainbow patterns. Sometimes they're showing things like flowers growing on the side of a building. And our idea for the project was that we could combine these 2 things. A real-time information about air quality or environmental quality with a dynamic building facade. And to do this, we started with a map of the city. We located the 27 different high-quality air monitoring stations run by the government. We redrew the map of the city according to air quality boundaries rather than geographic or political boundaries. Then we bent this kind of flat map into a kind of curved shape to make a physical structure out of it, a canopy to be installed in a public park. And this gave us what we thought of as a kind of prototype of a building facade of the future that would be interactive in 3 different ways. First, it would display air quality improvement. So it's a map of the city. Each neighborhood corresponds to a different panel of the map. And each neighborhood illuminates if its air quality right now is better than a year ago. So it's a low-resolution measurement of whether each neighborhood is improving or not. Number 2, it's a display of real-time air quality. So every hour the map goes dark, and the panels illuminate in the order of best current air quality to worst. So this is a comparison between neighborhoods. The previous version of interaction was a comparison of one neighborhood over time. And third, and what we think is maybe most interesting and relevant to the kind of life of the city, is that we invented a custom text messaging hotline. We allowed you to text in a postal code. And here's the important part. The panel corresponding to that postal code would blink twice. And then you would get back the information on your phone. So that's a kind of typical exchange of I have my phone, I'm requesting information, I'm getting it back, I'm engaged already in an ecosystem of information. But what we thought was probably more interesting and relevant to the future of building facades is that we can display on the building facade the collective interest in the environment. So the more blinking of this canopy, the more people are interested in air quality right now. If one neighborhood blinks more than others, we know that people are more interested in that neighborhood. And so the building facade, as a dynamic, interactive piece of the city, can be this kind of register of something that's normally very personal and hidden from others. So the building facade can play a kind of public role in the visual life of the city. And of course, this kind of physical construction in the city, which is a permanent kind of installation in a public park, takes on a life of its own, gets kind of used in different ways, creates a kind of artificial nature in the city, and a kind of ecosystem of information. It brings a layer of information into the built environment. 2, environment. So at about the same time we were developing that project in Seoul, we were also developing a similar project in New York City. And this project involved basically water quality and an installation in the water. But in other ways, it was similar to the one with air quality and an installation on land. More specifically, this project involved a floating network of lights, and they were half above water and half below water. Above water, we had dynamic LEDs, and below water, we had a range of different sensors. And this allowed us to create a kind of public interface to water quality, the way the previous project was a public interface to air quality. And we were using, in our first installation, this kind of stuff, which is now called the kind of material of the Internet of Things. So it's microcontrollers called Arduinos, and electrical wires, and physical sensors, and LEDs that blink and change color. But what we added to this project recently, and here's one example of how our ecosystem of design kind of expands over time in this organic way, we added to the project biological sensors in addition to digital sensors. And what I mean by that is that we added living mussels. So here's a tank of mussels, the shellfish same ones that we can eat in certain occasions. And you see these mussels kind of pulsing because they're opening and closing their shells as part of their normal metabolism. And it turns out that the amount and the rate that mussels open and close their shells is a very sophisticated and sensitive detector of water quality. And following that, we can take an inexpensive Hall effect sensor, glue it to one half of a mussel's shell, a cheap magnet, and glue it to the other half of the mussel's shell, and then we can harness the ability of the mussel to detect water quality and get a signal from it. I should note here that this does not harm the mussels, and it's a good question that I sometimes get asked. We knew about this approach because of some scientific papers that have used this approach for remote monitoring. And that approach relies on the fact that these wires hooked up to a mussel will not kill it and will not harm it from its normal ecosystem. And we're using that exact same approach. So it's another way that we're kind of expanding out and drawing on something from the scientific research community and using it in a design way. So no mussels are harmed, but we can put these mussels in their natural habitat, learn what they're doing in terms of opening and closing their shells, and get a very low-cost sensor for water quality. In fact, for about $2, we get a better indicator of water quality than a $10,000 dissolved oxygen sensor. But that's not really, I think, the most interesting and important part of this learning that we got from this project. What's deeper for us is the insight that we could maybe combine artificial intelligence with natural intelligence. In other words, we could combine the best the computer has to offer, the kind of holy grail of AI or artificial intelligence, with something that has existed all along but is a little under-recognized, which is a natural intelligence or a biological intelligence. In other words, mussels over millions of years developed this capacity to sense water quality, and we can think of harnessing that and combining it with the computer stuff to create a new kind of design palette that has a little bit of both. It's a hybrid approach. And we think that has a lot of potential applications for other projects in the future. So to mention a couple things about how our approach grows over time, here's our initial installation, which was actually a few years ago now. You see the lights changing colors because there was a tipping point in water quality, and you see the lights in the context of the East River in New York City, the Brooklyn Bridge and the Manhattan Bridge, kind of communicating information to the citizens. That project was a kind of test prototype funded by grants and an arts organization, but because it kind of gained steam as an idea, because a couple of people in city government liked it, it's now been commissioned for a 200-foot-long floating pier that will be permanent as part of the waterscape of New York. But what I like to say is that it's actually also part of the skyline of New York, because lights, even when they're flat, become part of what you see of the collective city from certain vantage points. So this is a rendering, of course. This is not real yet, but it's going under construction in the spring. And it's an example of how a prototype, a small targeted prototype, has grown into something bigger. 3, personal communication. This project was interesting for us because it was a kind of quick project. It was a project with a very low budget. And we were thinking about it after doing these projects about environment and digital technologies. And something that we really wanted to do here was to combine 2 aspects of the local culture. So this is a project for the cities of Shenzhen and Hong Kong for a biennale that they had a few years ago. And we were thinking, what could we explore here that would be relevant and interesting and kind of continue our research and push it forward. And we wanted to really make this site-specific installation, and we honed in on these 2 features that we found interesting about these cities. The first is street food, or the culture of eating out on the streets in these kind of pop-up food stands called daipaidongs. And the second was the manufacture of electronics. So this is a region where they manufacture LEDs, so low-cost electronics that we've been using in a lot of our projects, but they also manufacture cell phones, like almost all of the cell phones that probably all of us have been manufactured in this region. And our idea, and here's the moment where the kind of rigorous exploration of ideas gets intersected with kind of bizarreness of creativity. Our idea was to combine these 2 things by inventing a new electronic soup bowl that would be able to hide scrolling LED messages. So admittedly a weird idea, and I'll show you kind of how it played out. So we took these white plastic soup bowls that you can see in the photo here, and we used a CNC milling machine not to create some really complex form, but to shave away a very small amount of the bottom of the soup bowl. And the reason we wanted to do that is that we wanted to hide a scrolling LED badge in the bottom of a soup bowl. And these are electronics that are manufactured in Shenzhen, and we kind of hacked them to be able to display these custom messages that we invited the international artists and curators to compose. So we invited this kind of academics to create small manifestos or observations about the life of the city. We programmed them into these LED badges. And then here's the kind of hypothesis of the project. We thought that if we hid these messages in the bottom of a soup bowl, which would look like a normal soup bowl, but actually have this kind of secret in the bottom, then we could bring the technologies that we'd been exploring, like these digital technologies, out into the city in a way that was more about the subjective life of being in the city, the experience of the city, the culture of the city, than it was about something more objective and tangible like air quality. So here are a couple of the messages that were composed. These changed every week, and these were written by the kind of usual audience of the Biennale, the artists, architects, curators. But we really wanted to then collide this kind of ecosystem of the Biennale with street life. So we partnered with these local street food stands called Dai Pai Dongs. And here you see the kind of project in action. So suppose you were just coming to eat your dinner here at this stall. You ordered a bowl of noodles. You chose your vegetables and your meat, and you got some broth and some noodles. And you would then get this kind of before and after effect. At first glance, you would think it's a normal bowl of noodles, like on the right, but afterwards you would kind of discover something strange. And here's how it might be like to experience it. So you would see something maybe glowing at the bottom of the bowl at first, but you couldn't quite read it. And then you would look more closely, but have to eat some more of the food in order to get to the bottom of what's going on. And eventually you would kind of see this scrolling message. So in a way it was a project about communication and digital information and a layer of data in the city. But it was playing with combining this kind of international audience with local citizens, using humor and surprise as design ingredients, and involving, kind of trying to coerce some version of a conversation about the city through a small targeted project. 4, ecosystems. So for another project that was a kind of short-term installation, we were interested in seeing if we could kind of push the limits of what it would be like to design with less control, design something kind of open-ended. And this project, like many of our projects, started with a material. We like to test our ideas with materials out in the world. And in this case, we were fascinated by the material of honey. So you probably recognize this. If you take a jar of honey and you drop the honey back into the jar, it creates a kind of spiraling effect. And that's because it's a viscous liquid. And the interesting thing that we kind of discovered and we're interested in pushing further is that any viscous liquid will do this. And if you drop a viscous liquid onto a kind of conveyor belt, instead of having the viscous liquid just drop into a jar, it can create different patterns based on the speed of the conveyor belt. So if the conveyor belt is going fast, you get a straight line. If the conveyor belt is going slower, you get a kind of wavy line. And if the conveyor belt is going really slow and at just the right speed, you get very complex patterns like a figure 8 or other complex, more or less two-dimensional patterns. So that was one of the things we wanted to explore in building a kind of ecosystem where we would let it unfold without complete control. The second ingredient was a living material, which is basically moss, so a plant suspended in a liquid. And the third ingredient was basically information. So our idea was to combine these 3 ingredients in an ecosystem that we would let play out for 30 days without our control. In other words, we would design some rules, but we would not design a final result, and then we would kind of see what we could come up with over time, what we could learn about an ecosystem by designing its rules. So we had the synthetic material, which is the viscous plastic, the natural material, which is this moss suspended in liquid, and what we're calling a material of ideas, which was real-time web searches for the terms of synthetic and natural, and they all played out in this kind of construction here. So we built a conveyor belt. We built a machine to drop the synthetic material, which is recycled plastic, and we built another machine to drop moss. And so the moss and the plastic were both being kind of layered up based on how many web searches in real time were coming in about the synthetic and the natural. And the moss and the plastic were kind of competing against each other as this structure built up over time. In other words, the more plastic that was added up, the harder it was for the moss to grow and take hold. The more moss that was layered on, the harder it was for the plastic to attach to itself when it went around. So you're now seeing, you get a sense of the kind of rules of the system. We're building this kind of construction over time. You could maybe think of this as a bottom-up 3D printer instead of a top-down 3D printer. Most 3D printers, you know what you want, you program in all the precise rules, and you hope you get it right. In this case, we're saying, let's program in some rules, some feedback into the system, and let's see what emerges. And here's an example of about the first third of the installation. You see this kind of cylinder and an equilibrium building up over time, a kind of repeating pattern. But at a certain moment, because of a tipping point of the information and the materials and gravity, you get a moment of kind of chaos, a tipping point. But we're still playing out the rules, not intervening, not changing the rules. And eventually you got a kind of new equilibrium, which was, instead of extruding a cylinder, you got a kind of braiding of these bands together. And, so again, this is a project that is admittedly a little weird, but the idea that we learned from this was that, maybe it's not so unusual to be designing in a situation where you don't have complete control, where you're designing rules rather than forms, where you're working with some forces that are a little beyond complete control, and in some cases beyond being able to know what they are. But nevertheless, you can still push the system in a direction that you want. And that's something that we took from this project that we think is relevant, again, to our future work. 5, evolution. This is a project that was not self-initiated. A lot of these projects that I've shown so far were kind of self-initiated projects, but over time we grew into accepting some commissions and some kind of design challenges from big companies or small clients. And this is one example of that, and how we tried to keep pushing a research agenda, but through a kind of real-world commission for a big company. But before I describe the details of this project, I want to start with something that we had been thinking about around the time we started this project, which is that, of course, architects have been inspired by biology and trying to design with biology for many years, but biology of today is very different than 100 years ago. So 100 years ago, On Growth and Form by Darcy Wentworth Thompson, a very inspiring book for a lot of designers and scientists. But today's biology is stuff like this that I'm showing now, done by some of the people we've been collaborating with recently. So you can now visualize the neurons firing in real time in a tadpole, which was shown there. You can visualize stem cells and how they're sending molecular signals to each other in real time and determining whether to grow into bone or heart tissue or skin. And this kind of biology allows us to do some really different things than we used to be able to do 100 years ago. And we took this approach into a project which was basically a commission by the big airline manufacturer Airbus. So they have these planes, I'm sure this looks familiar to you. This is an A320 plane by Airbus. And Airbus is very interested in redesigning their airplanes, making planes that are higher performance and lighter weight so that they can save on fuel costs and reduce carbon emissions, so kind of big goal. But they want to start with components in the planes that they already have flying. And we worked with Airbus on a kind of design approach we had been developing, and they pointed us to this component shown in red here, which is called a partition. So it looks like a very mundane and boring part of an airplane, but it's actually a component of the airplane that has to undergo incredible physical testing and certification in order to be deemed safe to fly in airplanes. This is the partition that's flying today in the A320, and you see how in 0.4 of a second this partition has to be able to withstand 16G crash test. And you see, you can just watch the force by seeing this result in kind of slow motion. So it's a very boring looking component, but it's actually a challenge to design, in part because of the forces it has to withstand, but also because of some other geometric constraints. So here's the outline of the shape of the partition. It can only anchor to the fuselage in 4 points, and it has to hold that fold down seat for the cabin attendant. And on top of all of that, you have to be able to cut out of the partition this small shape that's shown inset here. And that's because if someone gets injured in the seating area of the airplane, you have to be able to put them on a stretcher and take them around the corner and out the door. And there's not enough room to do that. There's not enough turning radius unless you remove part of the partition. So all of that also sounds just kind of boring, except when you think about it, if a human was to try to solve the problem of how you would draw the structure for this component, you would put a lot of cross-bracing probably exactly where you have to cut out that part. So it is actually a challenging structural problem. And this is where we turned our kind of experiment and our hybrid design approach to an unconventional way to solve the problem. In other words, we started with a living biological organism. Here it's called slime mold. And the way slime mold grows in an adaptive network is it starts at a kind of center point shown in yellow, and it tries to grow out and meet those points that are the white dots. Those are sources of food. And it creates a network that is both efficient and redundant. It's efficient because it uses a small amount of material to connect all the dots, and it's redundant because if you knock out one of the bars, the system can route around the problem. And our thinking for this project was, well, that's pretty similar maybe to what you would need to solve the structural design problem of the partition. In other words, you might want a system that connects the dots of where you can connect to the fuselage, connects the dots of where you have to host the cabin attendant seat, and it has to be a structure that's both efficient and redundant. So we wrote an algorithm that was loosely modeling the logic of slime mold, not exactly the form, but the logic. And then we used the power of computing to encode that algorithm for a kind of biological slime mold program, then set up the computer to do what it does best, which is generate, evaluate, and evolve designs. In other words, a computer is great at repeating tasks if we can tell it exactly what the rules are. And so we said, start growing different slime mold-like networks, evaluate each one, and try to keep doing that for, say, 5,000 iterations, shown here, in order to find the results that are best at solving our criteria. And in this case, our criteria are minimizing weight and minimizing displacement under structural load. So all of these data points are a design option. We have about 5,000 design options shown here. And if we graph them in such a way that we want to minimize the x-axis, minimize the y-axis, because we want to minimize weight, minimize displacement, we get a huge set of designs, but we can also use the computer to kind of crunch through the numbers and tell us which are the designs that are the best set of designs at solving the problem, the designs closest to the 0, 0 point, and also color code the designs by what type of designs are, what the family of designs, what are the different ways of solving the problem. And at this point, we're basically able to use this kind of experimental approach to create the drawing shown in the center here, which is a kind of lattice of gray bars that are creating an adaptive network for the structure of a partition in an airplane. But just like nature, kind of has these multiple scales, we were also able to kind of use that same approach, and instead of creating each gray bar out of a solid stock material or a tube, we were able to create each gray bar in the center out of a bunch of tiny red bars shown on the right-hand panel. So we were able to do this multi-scalar approach. In other words, run the computational process again. So here's a zoomed in sense of what I mean. We take those solid bars, we zoom in and create a kind of finer grain of lattice, and then we, with those microbars, make them either thicker or thinner based on how much structural load they're carrying. This project was not only kind of hypothetical in the computer, but it was designed to test out an idea in the world. And so we combined it with some advanced manufacturing methods of 3D printing and metal, and actually with a new material, a new alloy that Airbus has invented for 3D printing of airplane parts. So we have now printed these parts with kind of advanced 3D printing in this new metal. You get a sense of what this looks like here. So it's a high degree of complexity. It's a shape and a design that would not have been possible to make by a human sketching or even a single human rule. But it's using this kind of power of the computer, guided in part by a kind of biological algorithm, to create a design that's a kind of hybrid that transcends any singular approach, and creates not only a kind of new direction for airplane design, but also a real bottom line benefit. So you can see in this diagram that the existing partition shown on the left weighs about twice as much as our design, and our design is actually even a little better at withstanding the structural loads. So this is a project for a real client that aimed to test some experimental technologies, but also to be real and to be certified for flying in an airplane. This is the largest metal 3D printed airplane part in the world, and it's undergoing the tests needed for certification in the next year or so, and will then start flying in the A320 airplanes. So that's a great kind of combination for us, the friction of the real world, including certification and manufacturing techniques and the size of 3D printer beds today, with the aspirations of this kind of far-out approach of biological algorithms helping us to solve problems in new ways. 6, open source. So another project that we did recently, this is for the School of Architecture at Princeton University, is the design of a small new laboratory building. So a small space to kind of do experiments. And part of our idea here was to create an open source building. And what I mean by that is that we wanted to create a building that existed as a kind of release into the world on day one, but that was very much designed to change over time, to be upgraded over time, and to be a kind of living experiment. And what I mean by that is that we identified early on with our clients, which are basically the School of Architecture at Princeton University, that just as in the biology department, across campus, they use an electron microscope to as their kind of instrument of research. Really, we could say that architects and engineers use a building as their instrument of research. So we tried to design a building that would allow this kind of research and be able to be experimented on. So how did that work? In a couple different ways. One is that the building was deliberately incomplete. And mainly what I mean by that is that it had a kind of structural frame, like every building has, but if you kind of go down and you see the progression of building this building to its completed form, you get to the bottom right, and you see that it's about 2/3 enclosed, like a typical building, and 1/3 unfinished or open frame. And this open frame is designed to support experiments and a kind of finishing the building over time by the research within the building. Also, we designed a number of systems in the building with swappable modules. And an example of this is that the building has radiant heat, so there are pipes for hot water in the floor of the building. And on day one, the building is going to get the heat from the waste heat of the building next door. So the building next door produces a lot of condensate. It's very hot. And we can grab that condensate, run it through the pipes in our building, heat up our building for no additional cost and no additional carbon emissions for heating, and then just put that condensate back where it was normally going to be sent from the building next door. So that alone is a sustainable feature, but I think, in a way more interesting than that is that the system is designed to be upgraded over time. So we knew that the researchers in the building were applying for some grants to create a geothermal well, and we designed the system in an open-ended way to be able to swap the heat from the source being the building next door to the source being a geothermal well in a very easy way. So it's designed to be upgraded without a lot of reconstruction, a lot of infrastructure cost. As I was mentioning before, it's also kind of rewritable over time. So the kind of surfaces of the building, the facade, the walls, and the roof are designed in a way that they're easily upgraded. Parts of the building can be cut out. New parts can be popped in a kind of quick release type of mechanism. And this is going to allow some of the research in the building over time to experiment with new types of double skin facades, new types of green roofs, new types of photovoltaic panels, and things like that. And finally, we built the building with the infrastructure to have a lot of physical sensors and to have a system to be able to grab all the data from those physical sensors so that different things could happen. In other words, there are sensors in the concrete, in the floor, there are sensors in the walls, there are a number of sensors in the airspace and in the ceiling, and all of these sensors provide data in order to inform certain experiments. So when a new type of green roof is added, you'll be able to measure the heat differential between the area with the green roof and the area without the green roof. So this is another way that we're kind of planning for change over time through allowing for data. This is a building that, for one, will host some robotics. So it's a big, open, flexible space. And we also designed this building with relatively low embodied energy in the materials. In other words, we made it out of wood, laminated wood instead of steel. And even though most builders, most contractors in New York and the United States don't really want to build with wood for a building like this, especially with the big gantry crane, it is possible, and we asked enough questions to prove that the reason it's not done is because nobody's done it before. So this will be a building with a 5-ton gantry crane made out of wood as its structure, and it is possible. And so that's another way that we're kind of pushing some of the limits and experimenting with a new construction system for this type of building. And finally, for this building, in a kind of fitting way of illustrating the interconnected loops that I was describing earlier, the final layer of the building, in other words, the facade, will be the first research project of the building. And what I mean by that is that the facade itself will be a kind of experiment in a new material and a new kind of building performance. So it's a kind of project within a project to complete this building. So more specifically, what I mean is that we're building the facade of this building, the final exterior layer, out of a salvaged building material. So you see here on the left, New York City scaffolding. This is how construction is done in New York for renovations. Super common. You see this all the time over sidewalks. Scaffolding is built. They use these big planks of wood, about 2 inches by 10 inches in cross section, about 10 feet long, and it's used outdoors. It has a demand to be structural, and it's typically used for about a year and then thrown away. But it turns out that some of this wood is perfectly good wood after a year, but it's much easier for the contractor to make a rule that they throw it out because of liability, because they don't want to spend the time inspecting the wood. So the first idea of the project was to take this material that would normally go into the waste stream, and see if we could do something interesting with it. And the more we thought about it, the more we thought that actually part of the problem of material waste is making rules of thumb, assuming that every board is bad just because some boards are bad. So we tried to hone in on what, how to kind of process different boards, what makes different boards unique. And at this point, we started collaborating with the researchers who are going to occupy the building, and they helped to identify 2 different experimental approaches about how maybe a piece of wood, if you look closely at its grain and emphasize the difference between the soft area of wood and the hard area of wood, and get a kind of micro contour in the wood, maybe that can have benefits for the thermal performance of the envelope and the hydro performance. I won't go into the details, but you can just see the diagrams at the top of how when the wind blows across a building, it takes away some of the heat, and that effect is stronger when it's a flat surface, and that effect is interrupted when it's a kind of wavy surface of microcontours. That's shown in the upper left here. In the center on the top, you can see how wood, or really any material with small divots in it, with these microcontours, will actually repel drops of water. Because the water has surface tension and it can't sink into the small slots of the wood. And finally, any wood has a kind of variation across its plank. It has knots, it has cracks, it has different grain sizes. And maybe instead of just treating wood as uniform across a piece of wood, we can kind of emphasize the differences and use them to our advantage. Our kind of insight here was to take scaffolding boards from New York City construction, try to analyze what's going on with each scaffolding board, do something to enhance the variation between the wood and its grain. And here we turn to an experimental approach of using machine learning. So this is basically a way of saying, how would we take a board and determine how it's different across its whole surface? Well, actually a computer can help with that. And there's some really interesting approaches right now of training a computer to detect patterns. That's how a computer can start sorting the photos on your phone into photos of, your friend versus your parents. And you can use that same technique to try to teach the computer to learn things about wood. And our first approach here was to say, can we train a computer to detect knots in wood? So take a picture of wood and determine where is the hot spot that's making a knot. So you see on the left a picture of the wood, you see on the right our algorithm trying to determine where there is a knot. And another picture and another detection, a kind of heat map. And if there's a picture of wood without any knots, then the heat map is not activated very much. Another one without activation, and finally another example of activation. So in this experiment, for a new approach to a material with variation, a salvaged material, we basically created this custom algorithm to detect knots in wood, and then created a kind of custom fabrication process to sandblast wood just where the knots are, because that's where the grain is the tightest, and created this kind of approach to treating a material that could be both a kind of look like this, a kind of aesthetic, but also a kind of performance benefit for the building, or an experiment in performance. Again, we had a bigger lesson from this, which was that with the power of computation and automation like robotics and automatic machine processing, maybe we can look closer into the performance of individual pieces of material and not treat all materials of one type the same. We composed the boards in a way that would kind of emphasize their variation and the knot patterns. And this is under construction now, and here you see an example which gives a kind of new aesthetic and also a new experiment in building performance. The second to last project here was one that we did where we were commissioned by not a kind of technical company like Airbus, but by an artist, in this case the musician Bjork. And we wanted to experiment with some of our same approach to materials, some of our combination of biology and digital technologies, but really put it to use for a really different effect. In other words, this is a project for Bjork's retrospective at the Museum of Modern Art in New York, and she had created a new song, a kind of piece of art for the exhibit, and she was interested in displaying this song as part of her retrospective, but she had always been a little nervous about hanging a song on the wall of a museum. It's not quite compatible. So her idea was to combine this song with an immersive music video and with a physical environment that supported the mood of the song. And our challenge was to create that physical environment. And in a way that is probably familiar to all of you as designers, our first idea ended up being our best idea. We did explore a lot of other ideas, but the first idea was to say, could we take the environment and make a physical version of the song? So we did a lot of different experiments, but the one that stuck was to take some software for music editing, create a 2D map of the song, project that map of the song onto the ceiling and the walls of a room that we were going to work with for the environment of this experience, and basically use that to kind of push and pull a three-dimensional topography and create a room that was really a physical version of the song. So how did we do that? We started with a kind of regular triangular grid. We distorted it according to the 2D map of the song. We distorted it in 2D, but then we also distorted it in the third dimension by creating a series of cones made out of felt, a kind of organic material that supported the kind of feeling and experience of the song. And we pushed and pulled the kind of size of the cones, the tapering of the cones, and the size of the opening or the tapering in order to create this kind of landscape. Some of our initial prototypes looked like this. And then we went into production basically combining a kind of digital model with a kind of automated digital fabrication and then a kind of handcrafted element to create, in the end, what was a kind of environment with this landscape of felt cones that created a mood that supported the song and the music video. And here's another thing that we're taking forward in other projects that used the tools of precision and digital technology, but didn't have that precise geometric computer look to it. And that was something that the client, in this case Bjork, had given us as a kind of design direction in a very enigmatic way, as you can probably imagine Bjork giving instructions. But it's something that we really thought we were experimenting with this in this project, and we were able to create something that, in her words, was not the look of the math and geometry of the 20th century, but had the look of something more biological and organic. And that's something that we think is, again, a potential technique or tool to mine further in our future projects. So here's the completed room. It had 50 different loudspeakers, each with a different mix of the song to create a very volumetric sound. And there were actually no lights in the room except for the film. And so when you entered the room, it was just a kind of blank black experience. And over time, as the song progressed and it became a little more light through the music video and uplifting in its mood, our kind of landscape of felt was revealed. And finally, to kind of round out the things we've been experimenting with recently, and in many ways this one we think has the most call for action in it of all of our approaches, is a project that we did for a competition and sponsored by MoMA PS1 a couple of years ago. And so, like many competitions, we had to create a vision for the project before we executed it. And this was basically a summation of our vision. This was a short video we created directly for the competition. This is the exact one that we submitted and used to kind of present our case. And this kind of explained some things we had been thinking about, a kind of far-reaching idea about ecosystems and environment and materials and new possibilities, but that was grounded in something that we thought was just close enough to real to be able to achieve. But remember, this is the competition. We didn't totally know if we could execute this, but we wanted to kind of sell it at the level of, this is a really interesting, forward-looking idea, but it's also at the intersection of what we can make a prototype of now. So really the idea of this project called Hi-Fi was that maybe we could kind of reinvent an approach to architecture by reinventing the brick. In other words, by making a material and a building out of that material with almost no waste, almost no carbon emissions, and almost no energy required. And the kind of bigger idea here was that maybe we could start with the Earth's carbon cycle, the kind of endless loop of growth and decay and regrowth, and maybe we could temporarily borrow from it in order to make the built environment. So maybe we could take low-value raw materials instead of high-value raw materials. Maybe we could spend only a small amount of energy converting those raw materials into building blocks instead of the usual approach of spending a lot of energy to convert those raw materials into building blocks. And maybe we could make a normal, useful building, and then at the end, and here's the kind of key, maybe we could return all of that matter, all of that physical stuff, return all of those bricks back to the carbon cycle instead of putting them into a landfill for 100 or 1,000 years. So it sounds very far-reaching, idealistic. What was our way of trying to experiment with this? Well, it was a living organism called mycelium. So this is a microscope video of the branching structure of mycelium, which is basically the root-like structure of mushrooms. And it turns out that you can take mycelium and combine it with agricultural waste. So not the high-value part of agriculture, not, for example, corn kernels that could be eaten, but the low-value part of agriculture, the chopped-up corn stalks. We could take that waste, combine it with mycelium, and here you can see a sped-up version. In about 5 days, it solidifies into a solid object of almost any shape. And this gives us a way to kind of harness a living organism, mycelium, as a tiny factory, as a way to make a physical material that maybe we could use for architecture. So there's some other people that have been using this approach for things like packaging, and our idea was to use it for an architectural brick, to make a new kind of brick out of this process. But no one had, at this point, made a large-scale outdoor structure out of this material. So, of course, we needed to do a lot of testing to see if it could work. We did testing of single bricks, testing of assemblies of bricks, and we were learning a lot about the material and improving it over time, growing it in different ways, experimenting with what was possible. And we did not do this only for research, although research was important. We did it in part because we wanted to build that building. And one of the first things that we learned, it should have seemed obvious, was that if you're going to make a 40-foot tall building, a 13-meter tall building, you need a structural engineer to vouch for it being safe. And if you want a structural engineer to vouch for it being safe, then they need to analyze it in structural analysis software. And if they want to analyze it in structural analysis software, they need to input a material for what it's made of. And we very quickly learned that there's no structural engineering software on Earth that has mushroom brick as a drop-down menu item to select. So we needed to gather the data and work, together in this ecosystem with the people who are helping to grow the material, the material testing lab at Columbia University, the structural engineers at Arup, our design team, to be able to figure out how to solve this problem, how to make a material that was robust enough, strong enough, weatherproof enough. We had a lot of iterations. We encountered some other challenges along the way, including that the material is much more waterproof on the outside than the inside, which means that you can't cut the material on site to make a complex form like you could do with some other kind of stone or brick. So we had to, at this point, use a computer algorithm that we wrote to solve two problems at the same time. There was a fitting problem. In other words, each course is a different length. How do you fit the number of bricks into the length of each course? But also there was a stacking problem, which means how does every single brick rest properly on two other bricks below it with at least 2 inches of overlap? And that was a very difficult problem to solve for this shape, one that we could not solve without a computer to help arrange all 10,000 bricks, to figure out the right placement and sequence of bricks. So like everything about this project, there was a very short time span. We had about 3 weeks to build it, and about one of those weeks it was raining. But we had to keep going because the installation was going to open on a certain day. An interesting thing to me about watching this in retrospect is that here's the point where we were taking, all of these ideas and combining them with a kind of ecosystem of labor and expertise and intelligence. In other words, we had Columbia University graduate students who knew a lot about computation and form, and we had New York City brick masons who know a lot about stacking things. And neither one alone had obviously ever built something like this before. So that collaboration, that exchange of expertise and ideas was another way of thinking about the interconnected loops of our projects that we kind of discover along the way. So here's a version of seeing our project in the context of the glass and steel buildings of Manhattan in the background and the clay brick buildings of MoMA PS1. This was a kind of medium scale test, about 13 meters tall with 10,000 bricks, to see could this really work for architecture. But we wanted it to not only be a technical test of this material, but also a kind of almost creative test. Like, what would it be like to design with this material? What would it be like to stand inside this material? What would the patterns of light and shadow be? What would the texture be? What would the kind of atmosphere be when you stood inside this project? Of course, the ultimate test of any MoMA PS1 project is its ability to host a party. And here was the first Saturday of the summer when 5,000 people came to the courtyard to see experimental electronic music. And of course, this was terrifying for us to have people touching and hanging on and picking pieces off of our bricks. But it was also totally fitting because, as I've been describing over and over, our idea for architecture and our idea of the interconnected loops, it was totally fitting for the test of this project not to be on a lab bench and not to be, on the corner of a vacant lot where a lot of facade mock-ups are done, but to be out in public, in culture, with people who had thoughts about it that we could kind of monitor, but we couldn't at all control. And that kind of mix, a project that had all of those elements, was something that we were really interested in pushing. To kind of prove the final aspect of the project, at the end of the summer, we deconstructed the tower, took all of the bricks and kind of crumbled them up into small pieces, combined them with food scraps and worms and bacteria and yard waste. And in about 60 days, all of this physical stuff, the entire volume of the building, returned to soil. And soil that we then used for tree planting, New York City tree planting, and also local community gardens, meaning that it was high enough quality soil to be able to grow food out of and eat that food. And in many ways, that led us to the kind of words for the big idea that maybe, as designers of the future built environment, we should be thinking about designing to disappear as much as we normally think about designing to appear. And that's certainly a thought that is in our minds and that we think has some potential to be relevant to a lot of aspects of the built environment, not just biomaterials, not just our kind of experimental approach. Thank you.
Thank you very much. I will ask you if you have some questions.
You have been able to construct computer algorithms from natural fractal organization structure. Would that be, do you think that that's been creating a pattern for that kind of exploration?
Yeah, I guess we think that we're really interested in mining the natural world for things like the algorithms of patterns, but also for their ability to detect conditions of their environment, like the living mussel, and also for their ability to make physical stuff, like in the last brick one. So I would say that we share with some other researchers right now an interest in using biology to create patterns, but I do think that we're a little bit different than some other approaches that seem to be honing in on a single formula for how to make projects. So we're more interested in the possibility that we could get a spark of a kind of idea or a logic from natural systems, and then feel completely open to the possibility of taking it in a different direction if that's more effective to solve the problem. So unlike some of our colleagues, we're not obsessive about biology being the only way or the best way to solve all problems or the most efficient resources under all constraints. In fact, some of the biologists we've been collaborating with have made us realize that actually there are a lot of inefficient systems in biology that just evolved for reasons of chance and mutation. So I know I'm going a little far from the pattern question that you asked, but we're interested in the patterns from biology. We think there's a lot of other ground to explore there, but we're also interested in, say, the patterns of crystal formation or chemical reactions. And we're interested in the combination of both, and patterns of math, which sometimes have no basis in biology. So, I mean, that's kind of the flavor of our approach. Of course, though, biology is such a rich, source of some of this.
David, you describe your work as dealing with not only with information but also with communication. So from that perspective, I would like to ask example about the form, the final form of your buildings. And maybe if you would like to go a little deeply in that relation, in that sometimes dichotomical relation between information and communication.
Yeah. Well, I mean, I think I like the kind of formulation of your question because it's similar to our approach. In other words, I think it's a relevant and good question to say, what does our practice think of form? Something that's been important to architecture, since it started and will always be important. But I think our answer is suggested by your question, which is we would like to put it in the context of a lot of other requirements and important goals of architecture. So yes, we are interested in form. We're not like anti-form, and we're not trying to downplay the importance of form, but we're trying to collide that with some other things that are also important. Sometimes maybe more important, sometimes less important. In other words, form is not only for its kind of iconic value or its kind of expressive nature. It could also be to channel airflows or to accommodate certain programs or to make people stop and wonder. Or I think there are many ways to kind of aim the form question. And even one aspect that we've been thinking about recently and kind of demonstrated by the final project I presented is that the form of the building is just one of its many forms. So in other words, there are multiple scales of form. There's the form of the unit, the form of the building, the form of the skyline, but also there's the form of the building when it's built. There's the form of all of that stuff before it was made into building materials in a building, and there's the form of all that stuff that's going to exist long after the building is used. And so we're, in general, interested in a more expanded definition of form. Not to say that we don't, think a lot about the form of that branching kind of tower, and but also to kind of give it some context in this broader consideration.
Yes, the question I think is linked with this question, because seeing the projects, form seems to be at the end of a process that generally is aiming to display information, but there's a certain step between the forms used, and inside each form there's many forms. So maybe it's one question divided in two, that is, how do you choose the form that you're going to use, and how do you choose ones that you display many chairs or many homes, push and pull, or the lattice.
Yeah.
How do you choose in both moments precisely?
Yeah. So the first question is about the system. How do we choose cones versus cylinder?
I think that the answer to certain typologies, or certain families, one. You have the lattice, or the grid, or the intersected cones, or the display orthogonal volumes.
Right.
How do you choose each moment or the distorted cylinder?
Yeah.
There is one could trace each certain families and make relationships. I'm trying to ask you, how do you choose in the first place this family, this typology?
Yeah.
Call it, and then once you're inside of it, when you're immersed in that process, how do you choose between? I think there are certain points where the efficiency and the redundancy, in some cases, is still leaving options open.
Yes.
It's just up.
That's a great point. In some ways, it's more straightforward to me to answer the second question. So, once we have a series of options, or, iterations. And I'd like to say that's probably true of all design processes. All designers have iterations, even if they are not computationally derived iterations. But once we have those, you're suggesting something that's exactly right and important to us, which is you can use the computer to identify the ones, or you could do this without a computer in some cases, but identify the ones that are very good. But then even within the ones that are very good, you have to apply some other criteria. So in some ways, the set of ones that are very good, or the best the computer can offer, is a range of options. And what we like to do there is engage human creativity and judgment and discussion and debate and intuition and the messy parts of architecture that we kind of actually very much cherish rather than try to diminish. So unlike some people who, in an engineering sense, would want only the highest performing design, we're interested in solutions that are above a certain threshold, like maybe 95% high performing, and then also offer something else, whether that's another criteria that wasn't able to be measured in the computer system, or whether that's just an idea of doing something in an unusual way to learn about a new way. And that framework for me is well summarized by what some people call the spectrum between exploitation and exploration. So when you're making iterations, especially kind of optimization-like iterations, you can use a certain approach, a kind of computational approach, to do exploitation, meaning you want to exploit small differences and get the single best result. Or you can use that same algorithm to try to get results that are pretty good performing, but that are unexpected and unusual, that you want to discover something new, and that's exploration. And we're definitely more interested in exploration. I guess for your first question, I think in many ways, even though it may seem funny for me to say this at first glance, we're very pragmatic. I mean, our ideas sound kind of weird and crazy sometimes, but we kind of like the constraints of any project in terms of like what's possible now, what can meet the budget, who's going to execute this, how will this play with our client when we pitch it to them. And so all of those things are very much part of our decisions about forms, both the kind of formal system or the typology as we're going. We like the multi-dimensional problem even before the computer gets involved, and trying to balance those factors and make judgments about it. So, I mean, in that sense, I'd like to say we don't have a formal project. We have some, kind of blind spots, or to put it more generously, kind of like things we've tried in the past that we like, and so we return to those. But we do try to approach each project with its set of, kind of opportunities and constraints, and try to invent new things. There's one other thing. You're probably seeing a little bit, and there's probably something in our projects of a unit repetition. And I don't know, maybe that a little bit comes from our putting material exploration toward the front of each project. And that is naturally conducive to a kind of unit-like approach, an aggregation approach. But anyway, it's a hard question for me to answer, but it's a good question.
Maybe coming back to his first question, I was thinking what we were chatting this afternoon during the tour, and when it's about the presumptions that you actually that you decide as a material to build up these algorithms. You proved that you are more than able to devise evolutionary algorithms that are able to build up a taxonomy of species within the exploration, and maybe the answer, just maybe the answer to how you decide which form are you going to choose is going back to the presumptions.
Yeah.
Because that's what the algorithm is constrained to produce.
Yes. I totally agree. I mean, you know, I actually sometimes ask my students this, because I sometimes use the same approach with my students. And I sometimes say, what % of your final result, and by that I basically mean the form, so I'm asking them the question, but it's hard for me to answer. But I say, what % of that form do you think is a result of choosing among 1,000 options? And what % do you think is a result of the system that you devised in the first place? Like either you're aggregating boxes or you're pushing and pulling cones, right? That system could never invent something that has spheres, or, you know, and it obviously gets more complex than that. But I do think that's right, and I feel like we're trying to be very aware of that in our studio. I mean, and in that sense, we consider the geometric system to be one of the primary sites of design. But designing the system, not the form. I mean, the system results in a family of forms, obviously. But that is creative. And that's why I think it's nonsense when people say the computer's taking away your creativity. You're making that system. The computer did not tell you to work with spheres or cones or whatever else you can think of. And so I think it does displace that, and not every designer might want to do that or feel comfortable with that. But I just object wholeheartedly when people say that's not creative.
Do you have a phase in which you stop and evaluate the results that are given to you and try to see what does that feedback to your prior predeterminations of the parameters of the system?
Yeah, definitely.
Like when you have the results of the fan, for example, for the airplane,
Yeah.
and you see like, okay, maybe this parameter I can add new, or
Yeah.
what's that feedback?
So we definitely do that a lot. In other words, and you know, we just did a project that I didn't show here, which is a design of a big new office space for a big technology company in Toronto. And the way I describe that to the client is, I show them, you know, our system that generated a lot of options. And I said, you know, so we created these options and we chose this one, but we actually created 7 other systems before this that had totally different results. So it's like each system generates 1,000 options, but we want to do more than one system, because how would we know if that's a good system? It's very organic, though, the process of when and how we do that. I mean, ideally, you know, one thing I actually told this client for the office space is, well, normally in architecture, if you're, you know, asking for a design for an office space, the architect might deliver 3 options. You know, and there's, you know, each one has a different story and a different layout and stuff. And I said, we're going to deliver 3 different systems, where each system has 1,000 options. I mean, it's not like we're trying to brag that we can create 3,000, but, you know, it's that's what the process requires. And we would do that, you know, just like other projects, you know, for as much time as we had, as much as we felt like there was something that we didn't try and learn from the other one. But we would want to kind of balance the, you know, the time and the likelihood that we'll find something new.
I was wondering if, what do you think about because you said that the muscles were not harmed, and how do you see and most of the projects, and usually these kind of projects in general, when they work with biological material as architectural material, tend to work with low complexity biological systems, to the point in which they offer less resistance to a certain ethics about
how do you turn biology into architectural material? No? Like you don't build with dogs or with rats or with whatever cheese, because that would be much more ecological, I don't know, politically problematic or something.
Yes.
So I was wondering how you see that, if you see the use of the palette of materials, if you want to call it as a low complexity palette of biological materials, as a question of ecological correctness, or as a question of the degree of evolution of the research that could grow in complexity in time, or how? I mean, or as a matter of kind of condition of the material that needs to be low complexity for some reason.
Yeah, that's a great question and a great formulation. I mean, there's a few different aspects to that I thought about. One is that it is important for me to take into account the non-human living organisms in the things that I do. And in that sense, I think it's likely to feel problematic to me to use some other organisms, like making a building out of dogs. But maybe not always. I think it would depend on some of the specifics. So I do think that's important, and I think in a broader sense that our designs and our approach are trying to take into account a broader set of stakeholders. I mean, not only the client, but the public, not only the nearby public, but the faraway public, not only the people today, but the people in the future, and not only humans, but non-human living organisms, and also a kind of ecology, bigger ecology. The complexity question is interesting because in some sense, I think it's exactly right that we're working at a moment of somewhat low complexity because that's the only way we can start. And a lot of biology is so complex that it's really hard to control, hard to predict, hard to use as part of a design palette. But what I think is that probably there's going to be a different kind of non-ethical or non-political branch of that question where bacteria, which are in some ways like they're low sentience, they're not, like no one would complain about using bacteria as a life, right? You don't complain about killing a bacteria. But some things that bacteria do are so complex that we still can't understand them, much less control them. So I think there's going to be an increasing use of that kind of process, which is increasing in complexity, which maybe we can, in other branches, maybe we can control it with more research, and that stuff is advancing really quickly. But I'm actually more interested these days in the other branch, which is maybe we can't control it. Maybe it's a black box. Maybe we'll never understand it completely, but we could still harness it. And that will involve us, again, re-engineering our own conception of ourselves as creative geniuses, as masters of control of our process. But maybe there's a version of a designer that's, like I was trying to argue earlier, more familiar with uncertainty, with lack of control, with a range of possibilities, and not, relying on your own genius to select the final one. A couple of other quick thoughts. I think there should be more discussion, frankly, about the implications of choices of materials and its impact on all kinds of life, including its impact on all kinds of life. So its impact on human lives, of course, and things like equality and distribution of resources and impacts of catastrophe and things like that, as well as animals. But I think we need to have that discussion more holistically. In other words, I think it's an easy target. I mean, this is a little bit of a weird analogy, but people who say they don't eat meat, then they get like the third degree about like what they do or don't eat. Do they ever wear leather shoes? And all of this kind of drilling down on those details. When I think there can be a range of responses, and you don't need to fully kind of ideologize your position all the time. So in other words, sure, it could be problematic to use organisms as sensors. It could be. In this case, I'm saying I don't think mussels are, but if we were using birds as sensors, maybe. But we need to compare that to the other approaches. That's what I think. And so that question should be asked, but it should also be asked of other projects. Like, what is the impact of doing nothing? Or what is the impact of a traditional project? And so I sometimes say it, we think maybe there are risks to working with biology in certain ways. Yes, but there are also risks to doing nothing. And those need to be compared in an open-ended way and debated. And so I welcome that debate. And I'm not, so single-minded about the use of some of these approaches that I wouldn't want them to be discussed and debated.
I was wondering, the entire presentation, you did not mention any reference to disciplinary references or history or installed topics in discipline. Even some projects are so far from architecture, like Zoom, Lake One, or even the last one, the only thing that was touching something about the discipline was the idea of the technique, the brick, and you don't talk about the form that, or the organization that building. So is that something that you think about, or is something that you're like, there's no discipline attachment needed?
That's a good question. I mean, it's definitely something that we think about, but I tend to describe about the projects the aspect that we feel is an experiment. I mean, that's kind of how I think of our projects and our practice, and I think you're right to observe that we don't tend to experiment very much in a project where the hypothesis of the project would involve a reference of the discipline. But that's if we define the discipline like we typically talk about the discipline, because in other words, the discipline also includes like how we make a unit and what the material properties are of a unit and how we've tended to make a brick in the past. Or so I do think we engage aspects of the discipline sometimes with different language and different emphasis, but also, I mean, I think you're right to note that some of our language and our approach is itself a hypothesis in a new kind of architectural practice that's a little more interdisciplinary, that's trying to frame its language and its projects in more of a, in ideas that are maybe more general public friendly, or sometimes more technical, but not in the architecture discipline. way of being technical, that are technical in some other way. I mean, it is, I think, relevant for me to think at moments about the role of our projects and our practice in the discipline. So in that sense, I don't feel like we're anti-disciplinary. But I do feel like we're in a way pointing at some different possibilities about future versions of the discipline.
What happens every time you finish one of these projects? Like, what's the kind of afterlife of each of them? You show a great variety of projects, but it's like you finish and afterwards, how do you give an end to that experiment and begin another one without continuing exploring of that? Because I thought it about the last project, like you said, like what would happen if you build these huge buildings with these materials. So my question was if you are like still doing research on that, or if you already finished and now you have like another next step.
Yeah, I think we don't have one set way of dealing with that. I mean, we do think about that a lot. But so sometimes a project will find a new life in a very similar, second version of the project, and sometimes that'll be right away, and sometimes it'll be a few years later. More often, our projects will kind of inform each other in a looser way. So an idea about an interface to the environment will be, kind of carried on in a different city and a different type of project, but we're still kind of building on some thinking that we had in the past. I guess it is relevant to me. I think it's worth noting that after some of the early projects that we did, I remember like very distinctly not wanting to be like the environmental quality firm, the public interface to environment firm, or and just now, we are doing some stuff with this mycelium material, but I also still don't want to be known as the mushroom brick firm, and just continue doing versions and versions of mushroom bricks and kind of productizing that and arguing that that's the solution to all our problems. But it leaves open maybe the follow-up question, which is well, how does that not just dissipate? And so we try to make an effort to share what we learned with other people. We try to make an effort in we're actually publishing a book now, and we want to kind of position some of it as not just about projects, but about things that other people might build off of, like a kind of workbook to our own, thinking. And so in that sense, I think we do aspire to be part of a bigger ecosystem of research that will push ideas forward over time and not have everything be a kind of one-off. But it's hard, and we're also a small firm, so we can't afford to have one division working full-time on sensors and one division working full-time on mushroom bricks. And, so we enjoy moving back and forth between projects.
I think we have another question. My question is about, it seems that most of the projects are funded through cultural institutions or grants or universities. Maybe not all of them, but there's a large kind of research funding and amount of research funding. So my question is, if that's the realm where you want your practice to be as a long-term project, or if that is, let's say, an aspect larger scale implications of this research just larger structures and larger collisions or larger scale impact of these kind of technologies?
I mean, the short answer is that it's a little bit of a work in progress for us. I think we are kind of at a moment of a little bit of transition from going from some of the smaller scale prototypes, some of the more temporary, more research-oriented projects to bigger ones. I mean, and just in very practical terms, with that are more permanent and bigger budgets and with a kind of bigger footprint in the world, conceptually. But I think that kind of feels natural to me, because even the early prototypes, as small and experimental as they were always meant to be about something that kind of could be done now, that was relevant now, that was about our building facades now. And so, as we're doing some, bigger projects and more kind of real world projects, I kind of welcome that and feel like that's kind of natural. And I think I'm actually looking at kind of the reverse question now, which is, as we're getting some bigger commissions and as our team is really focused on meeting those deadlines, and those are definitely important to our growth as a firm, how do we keep a foot in the experimental, in the culture funded, in the non big budget, non-profit driven projects? I mean, the project for the university was an interesting one as a kind of a transition project for us in some ways, because it was very much research oriented on the one hand, and we had the perfect research clients, which was another architecture school. But we were working with university facilities who are some of the most bureaucratic and pragmatic and real world people that you will ever meet. So I think that was an interesting bridge, and now we're starting to do some bigger projects, and I welcome that. I mean, I don't feel like we're trying to just create this comfort zone in the more provocative or experimental.
Yeah, I had a similar question, but it had a certain hypothesis that the work has something that, to me, makes it have a resemblance to Dillegan's Cofidio's practice in the 90s, and then how it evolved after. Obviously, with a completely different paradigm, and probably with a completely different prospect because of that. And with a different cultural agenda, obviously, and with a different insertion in the kind of debate. But with similar aspects, like the relationship to publication, the relationship to kind of research, obviously with a different tone. The non-profit research, so to speak, and then the association with cultural institutions, installations, and in a way the approach to biology, to me, is, one could see it as a second discourse or level of discourse to the question of conceptual or communication, the conceptual kind of condition of the work and the communication of the work. So, kind of given that resemblance, and maybe it's unfair, or maybe you don't like it, or maybe you want to differentiate yourself from that, I was wondering how, exactly the same thing, like how do you see your practice evolving against that model? Or maybe against another model that maybe I'm not seeing, but that's the one I'm seeing also because it's in New York and all of that.
Yeah. I mean, I think it's a fair question, but I do think about the differences that you stated, and I mean, in that respect, I mean, just being very practical, you know, a couple of notes. I mean, I think I like the fact that Diller and Scofidio continue to publish, that they continue to be involved in education, like you said. I don't think I would want our practice to ever be that big. I mean, I don't think it ever could be, but I think they grew very fast. And I think I do think that there is something about the ability to put together projects that also involve the right kind of client and agenda to make a point. So that's, I mean, I don't really want to offer any critique of Diller and Scofidio about this, but I want to note that as we're growing to, you know, a little bit in size and a little bit to take on different kinds of projects, I want to make sure that that we can continue to kind of advance our thinking and our agenda, which isn't super set, so it's a little flexible, but through different projects. So, you know, there's an example of a project that we're considering now, and I've really been thinking about and, you know, talking to people on my team about whether it's the right project for us. I mean, it'd be a well-paying project. It would be pretty high profile, but I'm not sure it's right for us. And I would like to say, I mean, everyone probably would like to be lucky enough that they can say no to some things that they don't really think are right. And that's something we're going through now. So, I don't know, in terms of growth, I don't see size or impact in the world as necessarily a compromise or a challenge to the mission of, you know, a firm like ours. But I do see that there could be some paths that seem to stray from what is most important to me and is most, I think, core to what makes the firm and the research valuable. I know it's a little abstract, but yeah. I mean, you know, at the same time, though, I think it's a great challenge to say how can experimental ideas have bigger impact on the world. I mean, I think that's an important challenge, in other words, not just an interesting challenge. So I am looking for that. I think there's a risk of kind of compromising in a way, but at the same time, there's a risk of not engaging, and so I don't want to quite do either one.
I think we have one last question.
In terms of growth, when you talk about like growing up in scale, sometimes you have to realize that you have to change from manual labor and like manual stuff to more digital fabrication. And I think there is a huge gap that there's still needs to be more like developed. How do you see that change between like manually putting the bricks and using more digital tools, you know, to like reduce, because bigger scale means like less people to be there and like do the huge technological stuff you have in the computer and making it real.
Yeah. I mean, I think it's a good point. If we made that one project with the bricks bigger, we would need a different approach. But I think that's I don't see it as like a conceptual jump necessarily, or like it's more of a gradient to me. And, you know, that would just become, I mean, I think we easily almost could have addressed that. And in fact, we did think, how are we going to lay all these bricks in time, and is there a way to have more aspects automated? And it was in some sense like a third automated and 2/3 manual, because we had some kind of automation in the layout and the sorting and things like that. But I think that would become just another kind of interesting aspect of the friction of the practical requirements of the project meeting the kind of research agenda. So, and I wouldn't be opposed to simplifying the design to make it bigger, you know, for example. So, so I think that kind of, you know, again, that kind of friction is something that we kind of welcome. I mean, the other aspect of the digital versus the handmade, I think that's actually really interesting in a lot of dimensions, not just practicality or budget, but like, what do we want out of it? What kind of labor? Because there's some parts of the world where, when labor is cheap, you know, labor is used instead of automation. Is that kind of job a good job? Is the look of precision better than the look of small variation of even the most, you know, experienced craftsperson? I think those issues are really interesting and relevant right now, but it's not a clear break to me. It's interesting. Okay.
Thank you very much.
Thank you.